And I tell you, that's much colder than what we were used to over the last couple of weeks.
Yeah. Yeah, September was very, very nice. I've just turned on, I think it is 2 or 3 days ago, I turned on the heating for the first time this year.
Yeah.
This season, heating season, of course,
Yeah.
in the beginning.
Yeah. I'll see what I can do. Maybe I can keep it without heating. If it improves again in a week, capacity of the house and so forth may help. But the temperature will go down. That's for sure.
Yeah.
Also inside.
Yeah.
If you have 5 degrees and a day temperature of 10, 11, your house temperature in 5 days will go from 20 degrees to 14, 13.
Yeah. No, but my wife is sitting very much still all day long, so she cannot sit in too cold. So I try to keep it around 20 degrees and then we manage from there.
Yeah, then 15, 14 degrees, you can't cope with 30 to 40 degrees. You get cold fingers and you get that. There's a sort of a limit at 13.5 to 14, 14.2 or something. And then your functions become more difficult.
Yeah, but it also depends a lot on your activity, because I remember when I was a technician, we worked all year round out, even in frost. It didn't bother me much. I got bad ears because I was always with open windows in the car because we had a little bit extra clothes, and then so I have sensitive ears. But we were working of course, when we were working at minus 12 degrees, it was a little bit hard for the fingers, but
but okay, that is working. But if I'm talking now about office work, so office, computer, things, smaller things like that, not much movement, then the 40 degrees is crucial. Under that, you give up. You can't even use the keyboard properly.
No, but my wife is, as I think I have told you, she has a disease, so she cannot move very much. So.
Yeah.
She can play a little bit of violin, but if it becomes too cold, the fingers become too slow.
But that's also, I don't think it's very sensible to do it. You have to keep a reasonable temperature that makes everything move smoothly. And whether that's 16 or 17 or 20, that depends.
Yeah, it's individual also.
Yeah. Another slide. Challenges in dairy processing.
Now he goes and speaking.
Is it now starting? Yes, it starts 10:32.
But they have put it on mute, so we cannot hear what they're saying.
No, I agree. And I'm after this person, it's me. Because
so I will turn off my picture so I don't come up. I wish you good luck for your presentation.
Thank you. I hope it still works.
Yeah.
One of them for more than 40, 50 years, and in multiple disciplines across the world, whom we have seen in the morning and today afternoon also, is very valuable. And exhibitors also and manufacturers, they like this concept. They want a knowledge sharing session, and we had a very, very nice session today morning on natural refrigerant, because that is where the shift is going. Because we talk about decarbonization, the sustainability, and all the various aspects we talk about. And we all know the importance of that actually in today's context. Now, talking sustainability and decarbonization sustainability in the context of air conditioning, which is comfort side, is okay. That is one aspect, because comfort we can say we don't have to maintain 24 degrees Celsius. We can go to 26, 28 on all that, because it is comfort for individuals. But here, when we talk about refrigeration and food processing, I think the temperatures and comfort, thermal conditions, whatever the environmental conditions, it cannot be compromised, because they are not human beings. They are livable things, and this, the biology, the chemistry of all that is very important. Where comfort, Japan says 28 degrees Celsius is okay. India, BE will say 24, 25 Celsius is okay. But here, there are no two temperatures at which substance can be stored. Whatever we talk about, apple or meat or frozen or whatever, frozen storage and all that. And there is a very challenging task of sustainability. Now, how do you conserve energy moving forward? Because decarbonization is the topic, is a high-flying topic today, where everybody wants to go. But it is how to address the decarbonization, how to put it into action. How do you turn that into action in our daily context? And this refrigeration and cold chain is again another important aspect of it. So in this refrigeration for food processing and cold storage, which is an important theme today of the afternoon session, what we have, we have 6 distinguished speakers with us. They are there. We have Mr. Aravind Surenge, Dr. Lambert, Mr. C.P. Charles, Dr. Alex, Mr. Alpaslan, and Dr. Omar. We have 3 of them. We have 6 of them sharing their thoughts on various subjects, and they have vast experience in this field. So we look forward to listening to each one of them in their area of expertise, and the topics have been selected very nicely by the technical committee of under Dr. Sukumar Devota and Dr. Saravanan. So we welcome all the speakers, and we thank them first for having allocated time, some of them who have traveled from abroad, some of them who have come from here in India. And we look forward to listening to your words of advice, words of, your knowledge sharing. Thank you so much. And we will proceed with the speakers giving the sessions, technical sessions. Thank you. I think we will have the introductory sessions by our MCs. And only thing is, since we have 6 speakers and 3 of them are online, we request you to keep the timing and proceed with that. Thank you so much. Thank you.
Thank you so much, sir. Talk number 121.
What do I say? Vannakam Chennai. And nationally, Namaste. It's always challenging, to talk after the lunch session for the audience as well as for the speaker. Yeah. But anyway, there is a time limit. He has repeatedly told us that. So we will start. Can you shift? Yeah. It's okay. I would only like to say that I have also been a past president from the past century. And I am an Ashrafil also. So which has not been mentioned here. So I'd like to say that. Next. Oh yeah, it's here. Well, friends, we are talking about the cold chain and the cold stores and all. Cold chain is an integral part of modern life. In fact, it's a lifeline for the modern world, as we all have realized during the COVID era, because it would have been very difficult to survive without the cold chain for food as well as for pharma products. This one, yeah, I got it. Thank you. Yeah, and as you all know, I'll show you some pictures here. Here is the gamut of. Okay. So, yeah, it's here. I can't see that. Well, we have a whole gamut of cold chain is shown here, starting from milk and milk products, fisheries, meat and meat products, poultry products, fruits and vegetables, ready-to-eat products, and the pharma and vaccines. So, sorry. These slides show, I don't know, something wrong. Why it's moving? No, no, I wanted this to stay. Okay. So go to the previous one. No. Technological glitches. Yeah, next. Yeah. Here we show the routes for the cold chain. The upper one. Not very friendly for me. Is it? No. Go back. Start from here. Yeah. Yes, this I have covered. The next one. Gamut also I have covered. Yeah. Yes. Stay there. No. The previous one. Next. Yeah. Here. Yeah. Here shows two routes of the under the cold chain. One is the chilled foods, and the other is the frozen foods. And in both these the pictures you see that cold store forms the heart of the cold chain. Cold stores, variety of cold stores. We have cold stores which are bulk cold stores, which are multi-product, multi-temperature cold stores. Yeah. Temperature cold stores. We have controlled atmosphere stores. We have distribution centers, ripening and all. So variety of cold stores are there. There is a huge potential for growth of the cold chain sector in India. India is number 1 in milk and milk production, number 2 in fruits and vegetables, and fairly high ranking in terms of poultry, meat, fisheries and all. And ready to eat, of course, has joined the sector also. And in pharma also, we are practically number 1. Yeah. But the cold chain operates, or the cold stores, they operate using electrical energy. Now that's a challenging thing. Every degree of cooling means additional energy requirement of 2.5 to 3.5%. So that's an issue. So as you go low in temperatures, you spend more energy. So that's another challenge in the operation of the cold chains. Now, what is the solution? Can I have the slide which shows the challenges? Yeah, this one. So these are the challenges here. Global warming to usage of refrigerant and leakage of refrigerant also. High electrical energy usage. Water requirement plenty. And even under the cold chain, we have the issues about the disposal of waste. Next. How to address these problems? How to address these issues? The solution to mitigate these issues is to work towards sustainability, to achieve best possible energy efficiency, and then finally aim towards net zero energy projects. Following the concept of net zero energy buildings in the first decade of the century, the concept of the net zero energy cold chain projects was also introduced somewhere around 2010. That was my first presentation. Next. Next. Yeah. Now there are various possibilities of using or sourcing the renewable energy. No, before that, there is one explanation to the net zero. Yeah, just go. Yeah, the concept of net zero implies that whatever energy is consumed by the unit in its operation on an annual basis is generated through possible renewable energy sources at the complex itself. Is it clear? So it's not that the unit consumes zero energy. We take a scenario of the whole world, I mean, whole year's energy consumption, and then see to it that that amount of energy or quantum of energy is produced at the site using renewable energy sources. Then what are the renewable energy sources possible? Next one. We have solar PV. I think everyone knows solar PV by now. Solar PV is a very common thing nowadays, right from residences to the large industrial units and even the cold stores. I'll show you some pictures there. Solar thermal. Solar thermal is also can be used for generating refrigeration effect. And we have systems which work on, for example, the absorption system, the adsorption system, which can use the solar energy by using hot water, very high temperature hot water, or steam generated through solar energy. And then we have wind turbines. This is very rarely used, but in case it's in the proximity of this particular location, then one can always think of using the wind turbine. Biogas or other waste agro products, the energy available from agro products, this can be used for running the refrigeration systems. So in order to achieve net zero status, it is necessary to assess the annual requirement, which is sourced from the electrical power, and then plan a renewable energy source on a yearly basis. Next. Now, what are the steps if you want to plan a net zero energy project? The first thing, in my opinion, is to design the project with sustainable technology. And what are the factors? The chief factors or the salient features of a sustainable technology is you have to have eco-friendly plant layout, efficient building design, highly effective thermal insulation. This is very, very essential, which is not really understood by many of our designers or engineers or even contractors. Sometimes they try to save money on application of insulation, but that's a very wrong practice. It is the insulation which actually maintains the temperature. The refrigeration produces that effect, but the maintenance of that cooling effect or the refrigeration effect is the responsibility of thermal insulation, which is always in action, every second, every minute, every hour, whatever. Next is efficient building design. Now, building design is very important. Normally, we in the cold chain sector, we don't think about the building design and all. So this building design is very important because the shape of the building decides how thermally efficient it is. A cubical shape of a project is most economical as far as the heat gains are concerned. Then we have eco-friendly and energy efficient refrigeration system, naturally. Use of waste heat recovery system. Some people have already explained that in the first session. Effective automation control and control systems. Today, there are control to control the controls. Energy efficient lighting and natural ventilation. Use of natural lighting also. Recycling of water and energy saving devices. There are several energy saving devices which give you substantial energy saving. And these can be discussed only when we can make a detailed presentation. Next. This is a picture which shows which are the points where energy is required in a cold store. There are different points. Like you can say, right, starting from the lights, the fan energy for the air cooling units. There is a condensing unit shown outside, which consumes this. Then there is a air-to-air heat recovery, where again some fans are there and energy is required. So all these points are there, and if you make a total of this, that gives you the energy consumed by the cold store. Next. Yeah, I talked about the points about the sustainability, and this picture shows partly some of the sustainable features related to a cold store. Next. Well, these are the possible sources of renewable energy here. You see the solar energy used for a small cold store. We have the wind energy, and we have the biogas, and where you can use the agro waste also. So all these forms of energy can be utilized in generating refrigerating effect. Next. We have vapor compression system as a part of refrigeration, which is common, known to everyone. The next is absorption system. There are two systems here. One is LIBR, lithium bromide water, where water works as a refrigerant. These systems have been developed to generate up to about -4 degrees. So it can also be used in the chilled cold chain projects. Then we have adsorption systems, which is a recent development in India. And this system purely works on agro waste. It can work on biogas, it can work on waste, agro waste like bagasse and all. So all that. And there is a demonstration in the last Refcold'. It was a live demonstration here, where the plant was running and maintaining about 4 to 5 degrees C here. So that was a very interesting development. And now, of course, that was a small capacity requirement, like a walk-in cooler. But now the development is going on for constructing larger units. Yeah. Next. This is what I just mentioned. Next. Refrigerant scenario. I think I will not go into the details of this because we have already discussed this in the first session. I would only say that there was a suggestion from Dr. Pramod Kumar about not recommending any synthetic refrigerant to substitute a natural refrigerant. And I fully agree with him. We have never done it in my professional career of 52 years. My total association with this industry is 60 years. But the professional association for designing is 52 years. We have never recommended any substitution of any natural refrigerant by a synthetic refrigerant. And I agree fully with Dr. Pramod Kumar. So ammonia will continue to be the mid and large size plant segment. Low charge systems will have a good this thing. Low charge systems have already been developed. We have done some 8 projects. One of the system got an award from UNEP and ASHRAE recently. And CO2 cascade, of course. This also has been discussed. Next. This is a test case. This is a case study of a 1,000 metric ton cold storage project. which should work as a net zero energy project. So on an yearly basis, there are cold stores, in India especially, where we have a loading season and where we have holding season. In the loading season, the product is cooled to the required temperature, and in the holding season, it holds the temperature and preserves the product to a much longer period. So here we assume that the loading period is 60 days, and the other this thing is 305 days, making it 365 days. So these are the figures here. 29,160 kilowatt hours as the energy consumed during the loading period, and 62,220 kilowatt hours during the holding period. So the total is 91,380 kWh. Now our whole aim will be to provide a renewable energy system which could generate this much of energy. Now, usually, we do have the electricity supply, and this can be done, especially if you are using PV cells, the photovoltaic cells, that you must have the electrical supply also, because then you can have the facility of net metering. Net metering, where you can supply your power when it is not required by your plant to the grid, and you draw the same power when this is not available. So this is the kind of energy that you need for operating this for the whole year. Next. So this is a sample selection as to what is the solar PV cell capacity, proposed capacity, 60 kilowatt peak. Then there could be modules, 240 watts, and there could be 264 numbers. Grid interactive string inventors. There is a set of it. The DC input is 63,000 and so much. And AC power output is about 60 kilowatt. That's what we want. And it is synchronized with the mains or DC power. So whenever this power is available, it will go straight to the grid. And whenever the grid power is not available, then we can draw once it is available and match it with the power consumed or power taken from the grid. So this is the concept of net zero energy. That as I said, on an annual basis, whatever power you require for the operation is to be generated by a renewable energy source. And then the best possible practical solution is the PV's installation with net metering. Because in other cases, if you don't have net metering facility, then you have to have batteries, which is an expensive proposition, cost of batteries, not only that, but the losses and also the maintenance of the batteries and replacement after a few years. So it's not a very practical solution unless it's a very small requirement. Okay, next. Yeah, this is a picture where you can see the an actual cold store somewhere in Rajasthan, where the whole roof of the building is covered with solar panels. And practical readings show that about 40% of the energy requirement is achieved through this. So that means the reduction in the electricity bill, which is a big advantage, yeah, commercially. Yes. Is the time over? Okay. I'll do before that. Yeah, next. So we come to the conclusion. Well, the concept of net zero energy building is a very welcome development. After the green building the movement, on similar lines, an attempt has been made to present the concept of net zero energy cold stores. The cold stores are energy intensive plants as the refrigeration systems operate at a fairly low temperatures. Time has come to move ahead not only for net zero, but net positive energy projects. And what is net positive? That means if you are consuming, say, a lakh of units otherwise, You try to generate 1,10,000 or 120,000 there and use that excess energy for some other purposes. So that is net positive. That should be the mission. And I would appeal to all of you, those who are engineers, designers, contractors, to join this mission for sustainable, innovative, net zero, and net positive energy projects in the cold chain sector. So thank you so much for this clearing. I think I have finished in time.
Yeah. Thank you.
Any questions? Yes. Yeah. A low charge system is something, normally in case of ammonia, most larger, mid-size and larger plants, they use the LP receiver. That is, there are high pressure receivers and there are low pressure receivers, and there is a pumping system. So a lot of charge is required. In the past, when this system was not in operation, they used to have accumulators. That was a gravity feed system. Again, that used to also have a lot of charge. But low charge system is based on the refrigeration compressors and air-cooled ammonia condensers, which is again an innovation. Yeah, air-cooled condensers. Nobody did that, those things there. And the air cooling units, of course, no distribution systems like pumping system or gravity system. We used electronic expansion valves. Yeah. And for reducing the energy consumption because of the use of the air-cooled condensers, we used adiabatic cooling using either the pad system, evaporative pads, or a fogger system, which is very convenient and yeah. So that's because of that, we could bring down the condensing temperature also. And I have cases where one of my clients has replaced or is added air-cooled condensers to his existing evaporative condensers because of these benefits. Yeah. And he uses air-cooled condensers more than the evaporative.
I have one question for
Yes.
you. Quick. What is the charge reduction? When you say charge reduction from the original, from 10 of refrigeration, what is the charge you have reduced?
Yeah. There is a chart actually. I wish I could show that in this presentation. But usually we consider about 7 to 8 kilo per ton of refrigeration. That was the normal thing with pumping system and all that with gravity operated. But here it comes to almost 60 to 70% reduction, where these systems are used with evaporative condenser. If you use air-cooled condenser, it is still lower. So there is a substantial reduction. Yeah.
Thank you. Thank you so much, Arvind Surange. And may I request Mr. MP Agarwal, who is one of our... Yeah, you have a question? Great.
Firstly, very, very pleased to hear that you've used adiabatic condensers. That's a great initiative. You talked a lot about carbon zero and net zero and so forth. Do you think we'll get to the point where one day output is compared to water consumption? So like in a country like India where water is scarce, we're focusing on net zero, but wouldn't it be great to say that this output was a per unit of water like they do in the beer?
Water consumption is an issue. We normally are using on majority of the major products evaporative condensers, where the water consumption is lesser when we use U-tube, shell and tube condensers with cooling towers. So water consumption in case of evaporative is lesser than what we spend in case of cooling towers. But as far as the air-cooled condensers are concerned, the water quantity, there is no water required for cooling without, for the condensation. But to keep the condensing pressure under control, we use this adiabatic cooling, which requires very small quantity, just about 10% of what it would have otherwise in case of evaporative condenses.
Yeah.
So that is what we have done it, and we have results on this. At least 8 projects are running on this design.
Thank you, Mr. Arvind Surangi.
Yeah.
May I request Mr. MP Agarwal to present a small memento on behalf of Refcold' India team to Mr. Arvind Surangi. So our next speaker is online and he's on the web. So, thank you so much, Mr. Arvind Surangi. Thanks a lot for sharing your thoughts on sustainable cold chain. Thank you, Mr. MP. Thank you. Now we will move to our next speaker who is online.
Talk 122. Refrigeration Technologies, the Sustainability Issue. Dr. Lambert, Agent, BV Environmental Consultancy, Venlo, Netherlands. Dr. Lambert is a member of the UNEF Refrigeration, AC and Heat Pumps Technical Options Committee. He has also been involved in various science assessment reports on the ozone layer. During 2021-22, he was a review editor for the Policy and Scenarios chapter of the Science 2022 Assessment Report. He works as a consultant with the Agent Consultancy Company in the Netherlands. He is a member of many refrigeration associations and the author of many publications, the latest on net zero issues for RACHP. Kindly take over the stage, sir. Author of many publications, the latest on net zero issues. Author of many publications, latest on net zero issues.
Can I start?
Yeah, yes.
Okay. So good afternoon at the conference, at the exhibition and so forth, and a good morning to certain people that are online. I'm going to deal with sustainability with the title, The Sustainability Issue for the Cold Chain Involving RACHP. In the outline, it says that we're going to deal with sustainability, what it actually is, developments on the Sustainable Development Goals, the SDGs. We'll look briefly at cold chain hotspots, at scenarios to reduce CO2, especially emissions from the food cold chain. We'll look at refrigerants, the SDGs that apply, and come to some conclusions. Just to go back a few words, sustainability has been used now for decades. However, the original sustainability, or Nachhaltigkeit in the German language, goes back to actually around the 18th century, and it applied to forestry. And from there, we go on and come to in 1972 to a book by Mr. Basler, who actually deals with sustainability in a broader sense to sustain the world for future generations. And you see the title page of the book, Endliche Erde, here on the slide. In 1987, Brundtland for the United Nations presented the book, a report, Our Common Future, that says that the development that meet the needs of the present generations without compromising the ability of future generations to meet their own needs was used. However, one cannot foresee the needs of future generations and how far it all fits. And the definition is therefore somewhat too short-sighted. UNEP uses now for more than a decade the following. Development is sustainable with the capacity of the capital to provide utility can be sustained in infinity. Whether that's something that is covering everything, I'm not sure. But let me spend one more slide on sustainability, where sustainability can be defined as the capacity to maintain or improve the state-of-the-art availability of desirable conditions and or materials in the long term. That's already, I think, quite okay. It can also be seen as a social goal for people to coexist on Earth over a long time, with specific definitions have varied. Being environmentally sustainable would then mean the degree to which a process or an enterprise is able to be maintained or continued while avoiding the long-term depletion of natural resources. That also makes sense. Choices matter. It is not possible, however, to sustain everything, everywhere and forever, because this is supporting the current planetary boundary discussion and the limits that we have here. How can we keep developments within livable planetary boundaries is a discussion that one often hears today. So sustainability is actually difficult to quantify. It may even be possible to really not measure it, not be able to measure it. So one uses a set of indicators to measure how sustainable something is. And that includes processes, products, services, and businesses. And I would also say here, and it's a bit of an introduction to my next slides, for many processes and products, emissions are already quite a good criterion. And then next, and the last comment on sustainability. Sustainability is one thing. However, it's also very difficult to define what is really meant by sustainability, sustainable development towards a certain goal. Once you can really define precisely what the goal is, the development in a sustainable manner towards it is not too easy to summarize. There are a number of diagrams. But let me say the following. The sustainable development concept has gained quite a bit of importance, we all know, and we focus on three issues: economic development, social development, and environmental protection. And the concepts, these schedules, these pictures here, as suggested below, are nice and different. However, it remains very difficult where to place sustainability in the midst of often very many parameters. So many people do not really prefer to use these. Let me say something different. And we start with a picture of two women in Colombia. In fact, these two at the foreign ministry in Bogota, in Colombia, came up with the concept, the idea of the SDGs, the Sustainable Development Goals. After that, we had the Millennium Development Goals that were not satisfactory. So they, in fact, designed it. It was then studied, completed, made more perfect for the rest of the world to look at it and to let scientists design the goals free from political interference. And it was in September 2015 that the current 17 SDGs were agreed to be done, completed by 2030. While the Paris Agreement, and we have been discussing 2 degrees and 1.5 degrees and net zero and so forth, was also adopted in 2015. You all know these, the 17 SDGs. To go to no poverty, to zero hunger, to go to reduced inequalities, to gender equality, sustainable cities, and so forth. Life on land that should be very much in order, life below water, and so forth. You all know this. I won't really elaborate on them. They started in 2015, and they should be done by 2030. We're now in 2023, halfway. And it's pretty certain that the SDGs planned for completion in 2030 are far from being reached. Delays of 30 to 70% are being concluded, where it's difficult to measure the precise status. But this is quite a delay of 50 to 70%. A flood of reports was published this year on how to go forward with the SDGs, particularly for the so-called SDG Summit held in New York at the United Nations a month ago. Of course, a declaration had to be written, drafted, and it was accepted, where governments declared to stick to their original plans to pay adequate attention to still achieve the goals by 2030. They also pledged to redouble efforts to accomplish this. However, the press releases generally said, we have some doubts whether the pledges will deliver. So the SDG discussion will continue. The SDGs, one will try to complete by 2030, but it's not yet done. And that applies also to food and so forth. One slide in between, how to assess sustainability, how to measure it. You need to go to 3 dimensions. You have to look at the environmental, economic, and social aspects. The main goals, what you think the sustainable development, the sustainable process should accomplish, need to be considered with the SDGs, and it should have a list of measurable indicators to actually assess which status sustainability has. And it's just a comment that UN agencies also have the SDGs as a guidance, as a starting point. One more graph, how to assess sustainability for the cold chain, because I have to touch the cold chain. It has taken long enough. 7 elements here. 4 of them may be country dependent. They're more overall: energy consumption, the use of mineral resources, to check whether standards and so forth. So that's mentioned here in the blue. I've made a choice based on items 3, 4, and 5, all emissions based, that will be dealt with here. Optimize the life cycle of equipment, check refrigerant phase down and phase ins, and look at possible demand reductions. To just show you again what we're talking about, the low level, we have the food chain. We go from harvesting to processing to distribution to retail to households. And higher up, we see electricity generation, we see refrigerants, refrigerant production, the equipment to be assembled, and the equipment in operation. That is, of course, the major phase. And we have reclamation and disposal. Now, the food cold chain and an example. The analysis will focus on the reduction of CO2 emissions from both food losses and from ACHP parts in the cold chain, the 2 major interactive elements. We're not going to take into account food waste. That's a different issue. All the numbers try to give you a good impression, rather than that I'm going to take generally about it. But they are just indicative. And we're going to see that we can make 4 cases: a starting point, a base case, a fully refrigerated cold chain, an improved RACHP in that cold chain, so to say, with higher efficiency and lower demand, and a net zero RACHP. And now we're going to go to pie charts and a few things. Now, left is the current cold chain with huge food loss emissions. There's, of course, refrigerant, electricity, and also some refrigerant emission losses. We go to the fully refrigerated cold chain, means that there's an enormous decrease of food loss emissions, but the refrigeration equipment losses, largely from operating the equipment, increase considerably, a factor of 3, I would say, not factor of 2 to 3. And we can improve it again, and we can improve further, that we get the same food losses, but we try to, over time, reduce the losses from the refrigeration part of the whole thing. The first step is 47% in this example, and a first improvement, and you can go further, is 8%. Let us compare this with the go to net zero. That's this figure. Again, 3 pie charts. The current cold chain that I just showed, the fully refrigerated cold chain. And now we go to net zero. The food losses remain the same. There are pro forma, almost negligible losses from refrigeration equipment and from refrigerants. So we see 3 pie charts here, with the third one to be expected in a net zero case also has, going from the fully refrigerated cold chain, a 47% decrease. That means from the original base case, we have decreased, in the case of net zero, 94%. These are numbers, I mentioned it, indicative, but it gives you a good example. Once more, in a table, you go from very high food loss emissions to very low ones if you fully refrigerate the chain, the cold chain, as it is then mentioned, not the food chain, but the food cold chain. We see that the refrigerant equipment emissions increase, of course, until we go to net zero, when there's only a pro forma figure of 4. And we see that the reduction in the first instance is 47%, and the 2 other steps, 8% and 39%, sum up again to 47%. So what I just mentioned, it only gives it in the table. But this is what it really is when you deal with it. And you can go further to lowering the charge, lowering the emissions. You can go to further higher efficiency and so forth. But this is the principle. It mentions it again in the white thing here below. Main issues to the cold chain hotspots I would still like to mention. For processing and cold storage, of course, we know all this, but I would like to repeat, we have to evaluate the life cycle and optimize equipment functioning. We have to maintain properly so that that equipment remains high efficient once we have it, and adapt the equipment functioning to changing actually requirements, changing food supply and food treatments. For transport, it's optimize the cycle in the freight compartments, optimize temperature levels for different foods, freight duration, and do regular maintenance. Again, maintenance is essential. For pre-retail or retail storage, adjust the temperatures where possible, look at the products you have, do very regular maintenance. Again, I have to repeat it, and that's certainly for the heat exchangers in and outside. And lastly, domestic. What is valid is to say, whatever the consumer can do, that is cleaning evaporator and condenser, and select the appropriate, not too low temperature levels for good function. These are main issues for the hotspots, at least. And let me then go to the current refrigerant choices. It wasn't dealt with too much by my predecessor, but still, for processing, we use hydrocarbons, we use CO2, and where not possible to use these low GWP refrigerants when there is maybe adequate non-flammability equipment designs not available, whether it's cost reasons to not do it, there may be local conditions. One can go to HFO 124, ZE, or it can go to certain HFC, HFO mixtures. How long the future is that they will have is another issue. For storage, low temperature, ammonia and CO2, and in some cases hydrocarbons, but it's dependent on the design, of course. There is one simple HFO in the 1132 isomer series available, not yet preferred. For processing, sorry, this is my mistake. Transport, low and medium temperature. There is many companies that still promote HFC, HFO mixtures like 452A, like 513A, and so forth. But there is definitely a solution. It's a solution in Germany developed, EcoCool, where hydrocarbons outside the truck, outside the reefer, and CO2 use inside may very well be possible at high efficiency. One could, of course, also, if one doesn't want to go to high GOP refrigerants, use two-phase salt solutions, but should, of course, avoid the use of R4,4B, which 4,4A, which has been so long used, especially in transport. For retail, CO2, again, hydrocarbons in the case of distributed units in the retail shop, and one sees after that the standard has been adjusted with the 500 grams and so forth, that there is an increasing use of hydrocarbons in retail. Of course, there is continued attention for some HFC, HFO mixtures, 454, 455, and I mentioned it before, long-term use is not very certain. And they can be used, of course, if there are circumstances that actually force you to use them. I don't need to mention 600A isobutane as a global choice for domestic refrigerators. Almost the last slide. How does this contribute to the current SDGs? We address in the food cold chain and the refrigerated food cold chain, especially SDG 2 and 3. We look at hunger, we look at good health, we look at SDG 9, infrastructure, innovation, we look at SDG 11, sustainable communities, 12, consumption and production, and 13, of course, climate action related to the emissions and so forth. Quite a bit. Plus, I must say, the Indian National Cooling Action Plan has the cold chain as an important element. So I don't think it's new what you all hear. Things are really under development. I think that India also is a very good example. India also has already a government department focusing on sustainable cold chains. Needs to be mentioned. And lastly, UNEP, the United Nations Environment Programme, also has a virtual cold chain exhibition running. Information is available at UNEP, of course. In conclusion, the better the food cold chain parts are designed, maintained and controlled, the lower the food loss will be. That will be clear. And further, the more low GWP refrigerant options are applied, efficiency will be applied in the equipment, the higher is the win-win. Both the issues mentioned contributing to a significant decrease in CO2 equivalent emissions, as shown. And lastly, it's also important that the applications in the cold chain further focus on possibilities for new refrigerant phase-ins. Look what's better, look what's coming up regarding the achievable efficiency, especially during the entire equipment lifetime. We have to look at the optimization of the life cycle of equipment as it is operated in the cold chain. Not mentioned too often, but it is an issue. Look at energy demand reductions via sophisticated strategies that can also relate to the food composition that people is cooling and processing and storing. And lastly, additional elements such as standards, if flammable, etc., refrigerants will be applied. That needs attention as well. And I think with that, I could say thank you.
Thank you. Thank you, Dr. Lambert. We have a packed full house today listening to your presentation. Any questions? Any delegates? Anybody wants to get clarification from Dr. Lambert? It has been a wonderful presentation, Dr. Lambert.
Thank you very much.
Lambert,
and I think it was less than, we're still reasonable on time.
Yeah, very much. This is Sukumar thanking you personally. Thank you very much for accepting our invitation.
Sukumar, you're welcome.
Thank you very much.
Yeah.
They have closed the session. Okay.
Okay.
Now we will move to the next topic for us. Now we have challenges on dairy processing and storage. We have Mr. Charles with us. who will take us through his learning, and he will share with us his expertise and what he has. Welcome, Mr. Chan.
Talk 123, Challenges on Dairy Processing and Storage. Mr. C.P. Charles, Member Central Executive Committee, Indian Dairy Association. Mr. C.P. Charles is a member of the Central Executive Committee of the Indian Dairy Association. He has a rich experience of 42 years in the dairy sector. He is the director at Denmark Training Academy and regularly conducts skill development programs on sourcing, manufacturing, and marketing for the dairy sector. He serves as a consultant for the dairy sector and is a national level resource person at FSSAI. Kindly take over the stage, sir.
Thank you. Vanakkam, namaste, and good afternoon. At the outset, I thank ISRE for just inviting me to this technical seminar. I should thank Mr. Sridhar and Mr. Shankar, who have been just continuously contacting me to be here this day and talk about the challenges in the dairy sector. I will just take you to this small, picture here. Our biggest challenge is, I think this pointer is not working. Okay, the biggest challenge is from the cow to the cooling or chilling, we call it. Sorry, it is not working in that. No, correct. It's working, but it has to work there now. It is. Okay. The biggest challenge we face today is the time taken between milking and chilling. See, we have been facing problems in this sector because the time taken from milking to, here I have shown you a bulk milk cooler, which is nothing but a cooler. It is not a chiller. It's almost 4.5 hours from the udder of the animal to the cooling equipment. So what happens in between? This cold chain is not maintained because in India, we have production of milk by masses. It is not mass production like European countries or America. So we have 8 crore or 80 million milk producers who are involved in this milk production operation. So they produce, according to the government India statistics, it's around 8 kg of milk per day, or we'll say that around 7.8 liters of milk per day. So this is all aggregated and then it was just collected in a place and then it is again cooled and sent to a common place for cooling. So the time taken is the biggest challenge. If you look at the quality of milk from the udder of the animal, it's excellent. I'll just show you a table where we have conducted a study. We find that the number of bacteria, live bacteria present is very, very limited. But when it reaches the cooling center, it becomes manifold. And you remember this man, the great man, Dr. V. Kurian. Today, India is #1 in milk production in the world. We have just touched 221 million metric tons of milk production. And we continue to be. Last 26 years, we are #1 and we continue to be #1 in the world in the coming years too. And he laid the foundation in 1970, it's Operation Flood. So today we are in this position. So I'll just take you, I told you it is around 221 million tons we have in milk production. We have world, we have around 23% of share we have. And India is the only country where 77% of the consumer rupee is passed on to the milk producers. Nowhere in the world this much of percentage of money is passed on to the milk producers. That's why in India, people are continuously interested in producing milk because the money which is flowing to the villages is once in 10 days or once a week. This is a continuous cash flow to the villages. So it takes care of the livelihood. And let us look at the market trend. See, market is improving. Around 85% of the urban population is consuming milk, and 78% of the rural population is also consuming milk. And if you look at the liquid milk is growing, market is growing at the rate of 16%. It's expected to be next 5 years. And the consumption is also increasing. So the challenge is becoming more and more severe because milk is a perishable commodity. It has to be processed or cooled within 4 hours in order to retain its quality. Consumption is 265 ml per day per person in the country. It's likely to be increased to 592 ml per day per person in the country. And our dairy market size is going to be 31 lakh crore by 227, 308.4 million rupee by lakh rupee, by 2027. So now let us come to the real challenges. In packaged food retail market, dairy is the highest share. Dairy products has the highest share of 38.2%. But most of the time you find we supply refrigerators, we supply VC coolers, we supply chest freezers, and most of the time we find that along with milk and curd and other products, coriander leaf, curry leaves, chili, everything is kept inside. This is again a kind of education to be given to the retailers. Ice cream is India is increasing its share, fastest growing market, 13% on a year we are growing, and ghee export is also. So far, foreign countries were not taking ghee from us. Now slowly our export is increasing, and our love for dairy products is also increasing year on year, and as a result, consumption is increasing. This is the most important part of this presentation. So, which is giving us more margin? You look at it, curd is a yogurt, we call it in foreign countries. In India, we call it curd. 18 to 20% growth, or 18 to 20%, margin. Look at cheese, 17%. Flavored milk, buttermilk, 13%. Butter and ghee, 9%. And only milk is only 5%. Liquid milk is 5%. So value-added milk products is just giving us more margin, and these all require a good cold chain, robust cold chain, or else the entire product quality will be a big challenge for us. Now let us look at some of the opportunities. We have so many dairy plants in the country. Look at it, 2,277 dairy plants we have in the country. Private sector has got more dairy plants than the cooperative sector. And this is likely to increase because Government of India is just envisaging, and that should go, the total capacity should increase to around 8,401 tons per day in drying of milk, and value-added products around 20,534 tons per day. And share of dairy is the highest in the food processing sector. Look at the procurement scenario. You look at it, privates and cooperatives, almost equal. Privates are little more than the cooperatives. So let's look at why cold chain is required. Why do we require cold chain? The first thing is temperature. Look at it. The bacteria grow very luxuriously above 5 degrees centigrade up to 60 degrees centigrade. So we have to always maintain below 5 degrees centigrade. It becomes a biggest challenge for us. Most of the dairy people think cooling and chilling both are same. Though we just go on educating them, cooling is different and chilling is different, but people are just finding it difficult to understand it. Look at the bacterial quality of raw milk. Raw milk is the milk which is drawn from the udder of the animal. You look at normally we use a terminology called methylene blue reduction time test. That is a test we normally use. And you look at the standard plate count. From the udder of the animal, the SPC is only 3,000 to 20,000. colony farming units per ml. Maybe I will be using some of that term, which will be very difficult for some of us to understand, but still there is no option for me. But when it reaches the dairy dock, it comes to 11 lakh. 11 lakh. That's the biggest problem we face. That's what I told. We have the biggest problem of maintaining the time and temperature, the difference. Then, sorry. I think you have to reopen it. Now, why cold chain? See, our raw milk, now we are just talking about chilled milk. So far, I talked about the raw milk. Now I am talking about chilled milk after it is brought to the bulk cooler and it is cooled down to 4 degrees centigrade. Bulk coolers are designed in such a manner that from room temperature, the milk first phases to 10 degrees centigrade, then from 10 degrees centigrade to 4 degrees centigrade. So the bulk cooler capacity is a tank. It is nothing but a big refrigerator. So you have 5,000 liters capacity. We tell our people, you have to fill only 50% of it in the morning and 50% in the evening. But what our people do, 100% they will fill in the morning and then empty it, they fill it again 100. So again, education. It's really a challenge for people like us in the industry. Okay, what is happening? Cooling is taking place gradually. As a result, the bacteria grow. So if you look at it, pooled raw chilled milk, this is taken in a place like Gujarat, where the study was conducted, and it is close to 2 million bacteria per ml. Now, what is the outcome of it? Now, spores will just grow. This is a kind of, they survive even pasteurization. We pasteurize milk at 72 degrees centigrade. And we hold it for 15 seconds and immediately chill to 4 degrees centigrade. Even the spores, survive and they multiply fast and then they spoil the milk. Why cold chain? Cheese. We know only 2 types of cheese, processed cheese, and now we have mozzarella cheese. But there are 1,359 varieties of cheese in the world. And we now know about cheddar cheese. Some cheeses which are imported, like Swiss cheese, Camembert cheese, Gouda cheese, all these cheeses. But our quality, because of lack of cold chain, we are not in a position to manufacture all these variants of cheese because our microbial enzymes, which are produced by the bacteria, they survive heat treatment, they survive processing, they produce off flavors and spoil the product. And this is the most interesting factor. The pouch milk which you get is pasteurized. According to me, I am a dairy technologist. I say it should safe for consumption. But how many of us have got the courage to take it without boiling? It's a big question to us. Why? When it is possible, only when we have a kind of, cold chain without any post-processing contamination, then this is possible. You travel to any foreign countries, I think some foreign friends are here. You can take milk because I traveled many countries. I took milk as without even just boiling. So this is the biggest problem. Our quality of milk is good, but we are not in a position to maintain the cold chain. This is the biggest challenge we are facing. Okay. Now this is the demand growth. Now let us look at some of the opportunities because you're all from the refrigeration industry. I should also tell you instead of challenges, some opportunities for you also. This is the estimate prepared. You look at it, we are able to cover only 29% share of the demand in the southern states of India. I have not taken the entire country, only southern states. Look at Andhra Pradesh and Telangana, only 19% we are covering. And Tamil Nadu, only 33%, Kerala 27%, and only Karnataka a little higher. So there is a lot of, scope for, improving the industrial, growth and the support from the refrigeration industry. And another thing which is growing very fast is the bottled milk, which is growing at 16% per annum, which definitely requires a cold chain. Without that, this milk cannot be sold. Butter and paneer growth is 18% per annum. You know very well butter requires -18. But most of the time we find that butter is stored at only 4 degrees centigrade. Okay, paneer should be stored at 4 degrees centigrade. And as you are aware, paneer and cheese are the only non-vegetarian protein available to the vegetarians. Cheese is growing at 25% per annum, and there are different variants, varieties of cheese, and this has to be ripened or cured at 8 degrees centigrade. We require a cold chain for it, and it has to be stored after curing at 4 degrees centigrade. Flavored milk, the growth is 32% per annum, but it doesn't require any cold chain because it's a sterilized milk. It can withstand at room temperature for 180 days, but it has to be served chilled. Then only people can just take it. So we require a cold chain for it. Lassi, which is, you call it a yogurt drink in some countries, but we call it lassi, is growing at 28% per annum. It's on turnover basis, I'm talking, not on the volume basis. So here we require a cold chain. Curd and yogurt, growing at the rate of 32% per annum. This is the biggest growth. If you look at any industry, any private dairy in South, you will find that curd growth only has supported their bottom line. So today, our people have forgotten how to make curd in the home. They all purchase curd. And ghee, it is 12% per annum. Now you will all be astonished why ghee cold chain is required. I will just explain you why it is required. It is growing at rate of 12%. Now you can see this ghee, top portion, what is called, it's called granulation. That is the most unique nature of ghee. If the ghee is what you call watery or oily, you may not like it. It should be grainy. In Tamil, we call it manal manalai. It should be like sand. Now, what are the supports needed? Now, look at it. First thing, average time to milk. I already just explained you. From the farmer to the chilling plant, it takes 5 hours. So the growth of bacteria is. So what to do? How we can address it? So this is the money involved also in it. So we are spending more money on it, transportation, commission, etc. So why not we think like this? A kind of transportation come chilling. Can we not instantly chill the milk when you collect it from the collection center? There are collection centers. Why not a van goes to each and one company has tried this. That's why I put this picture here. It can simultaneously chill the milk and also it will just transport the milk. There is another thing which is just we tried in some company. Milk cooling at the producer house. This is like an immersion heater. So why not we try this? This is yet to be popularized. There are few takers for it. So the company is not willing to invest money on this mission. Another one is can cooling at the collection center. No, we collect milk. See, some 200, 300 liters we collect in a village center. So they have a kind of can cooling system at the collection center. This will also reduce the growth of bacteria and improve the shelf life of milk. This is another photograph. Recently, I have seen, I put the company name also. This is I have seen in the last, I think last March, I have seen this. See, they pour milk in the top and it comes down at 4 degrees centigrade. This is what we require now. We want instant chilling of milk so that the quality of milk will be retained. We will be able to manufacture good and quality milk products in our country. And this is the cold chain. Normally we maintain, we have bulk coolers, we have what you call milk tankers which are insulated. We have mini milk packaging station. This is how slowly it is coming up. See, the opportunity is ready to install IBT. See, if you want to put a IBT, ice bank tank, it requires a lot of time, civil construction, this, that, everything. Finally, there will be some problem. You will not be able to purge the oil somewhere, ice will bucket. So this kind of, ready to install IBT will support the industry. Walk-in cold rooms. I have seen many walk-in cold rooms in this exhibition, walk-in cold rooms. And of course, there is a pasteurizer, it is a skid-mounted pasteurizer and a packing machine. So why it is, nowadays people are asking for fresh milk. So you can, as per the Food Safety Standards Authority of India, you can sell raw chilled milk as per the standards. Of course, you know this because these are the things, now slowly the top right one you could say is find that, stacked storages because, we have, shortage of space. This, very well, automated storage and retrieval system. In many cooperatives, they have started, and in privates also, they just install this system. It's little expensive. Initial is very high. Initial investment is high, but it really saves money as well as energy as well as the manpower. This is another thing, which we tried in some factories, deep chilling or glycol chilling. Why it is necessary? We can just chill the milk at 1 degree centigrade or 0.5 degree centigrade, pack the milk, and then store the milk at 1 degree centigrade in the cold room, then transport. So less than 100 kilometers radius, you can send the milk without the reefer truck. This is the main advantage, and many companies have started this, glycol chilling or deep chilling. Curd, we require cold chain. First is we require incubation room, 42 degrees centigrade. We require blast coolers. We have to bring down the temperature from 42 to 4 degrees centigrade. Our spiral coolers or curd cold room where we maintain 4 degrees centigrade. This is very important. Otherwise, the curd will not have the proper consistency. There will be way out in the curd and curd will become watery. Cheese and paneer manufacture, I already explained to you, it is 8 degrees centigrade ripening and storage of paneer and cheese at 4 degrees centigrade. This is very important. Ghee granulation. How do you granulate the ghee? You cannot even suddenly cool the ghee. If you suddenly cool the ghee, it will become pasty. It will become sticky. You have to gradually cool the ghee. So what we do, we keep after the ghee manufacture, one day, one night, we keep it outside in the room temperature. The next day we keep inside, slowly cooling to 26 degrees centigrade in 4 to 6 hours time. The granulation will be excellent. So here we require. What we do, traditionally what we do, we put some ceiling fan or pedestal fan, we keep the windows open, close, these kind of things. Now, this kind of system is really helping. Many people are following this. Milk powder. Normally we say it's a powder, the skim milk powder, which can be stored for 1 year without refrigeration. You store with 24 to 20 degrees centigrade with 11% humidity, it can be stored for 2 years. It can be stored for 2 years. So again, we have this kind of transport system, fresh, chilled, frozen, ambient. So we have a lot of opportunities in this. And this door delivery. Now we started door delivery. We have only taught Amazon, everyone, how the door delivery to be. Only the milkman taught them. And today, we are not in a position to do that. So this is, I think, I taken, again, I used Madhusudan, and sorry. This is a paneer dahi. Along with that, this is a chill pad, box. They are just using it. And this is how now distribute packaged milk with gel pack. In Kerala, many people are asking, our distributors, our retailers are asking this, and we are just supplying them. Maybe it is little expensive in the beginning, but still, they will be able to maintain. This cold chain should be maintained. Now look at it. I removed all the names. Abuse of cold chain. You may go for 1 degree centigrade, deep chilling of milk, packing of milk, storing of milk at 1 degree or 2 degrees centigrade. You may use a reefer truck. Finally, it comes to the platform. This is the biggest problem we face. This is how it is. So future of industry, I will just put food industry as a whole. It is growing than the general industry. The growth is phenomenal and it drives urbanization. And as a result, it's direct benefits to the industry. Consumption increases. And as a result, you have a lot of opportunity in the global market. Only thing is our cold chain has to be maintained. I think this is an appeal to all the refrigeration people, engineers, designers, that please suggest us cost-effective method of just reducing the time between the milking and cooling or chilling. Thank you. Thanks for the opportunity given.
Thank you. Thank you so much, Mr. Charles, for taking us through the entire journey from எங்க இருந்து பால் கறந்த அப்புறம் எப்படி இது பண்றது அப்படின்னு. Very nice of you to share with us. Any questions from anyone?
Yes. Yes, sir.
Sir, what should be the shelf life of the milk when it is sold in pouch by the dairies?
See, it is written very clearly in the pouch. You store at 4 degrees centigrade, 48 hours.
48 hours. But the mother dairy in Delhi, they sell a small pouch and they say the shelf life is more than 1 month. So do they add some preservative in that?
Extended shelf life of milk. That is called ESL milk. That is it's not a Tetra Pak. Tetra Pak will be
Not at
180 days. It's ESL pouch. There's a ESL pouch which is now introduced. Not only with mother dairy, many companies like Vishaka Dairy, everyone, they give 30 days. But it can go up to 60 days also. It's called extended shelf life.
So is there any difference between the small pouch and other pouch?
Because here we only pasteurize milk, 72 to 75 degrees centigrade. We heat and then maintain at 15 minutes and 15 seconds and then chill it to 4 degrees centigrade. We give a thermal shock to the bacteria, and the index organism is Mycobacterium tuberculosis, that is killed. So once it is killed, all the disease producing bacteria are supposed to be killed. Okay. Whereas here the temperature is higher, 120, 121 degrees centigrade they kill all the bacteria, so that the survival is given up to 30 days.
And
Your
then
shelf life.
Then they chill it down.
Huh?
After
No, it is not necessary to chill. You can keep it as it. But you are telling a pouch milk in chilled condition or in a room temperature?
no, there is small pouch which is sold by mother dairy. The shelf life is more than 1 month.
That is extended shelf life milk. ESL milk we call it.
Thank you.
Any more questions? Yeah, quick one.
So good afternoon. Sir, according to you, what will be the feasible solution for chilling the milk in quicker way? Is it would be production getting more production at the same place, or making like mobile milk cooler like that?
See, mobile milk cooler is one of the solutions, but in India, it will be very, very difficult. So what we do, we only train our milk producers to milk the animal 30 minutes before the collection starts. And the collection center will work for only 30 minutes. It's not applicable for cooperatives. Cooperatives, 100 people will come and pour milk. It will take 2 hours to collect the milk. Whereas in private, we would be able to control that. So once it is collected, we say that within 2 hours, it should reach the chilling plant. So then we will be able to control. That is the only solution currently we are doing. But our issue is something else. Our issue is, there are many things connected with that. Availability of water, disposal of water, availability of power. I think our previous speakers have explained very nicely. We are also using solar power for our bulk coolers. We have started using. And some of the big dairies in South, they started using solar power for running the entire dairy plant. Slowly, we are just moving towards that. And we want to also economize because currently 30% of the power is spent on refrigeration unit in a dairy plant. When I was in college, we were taught 60% for the energy is on for refrigeration unit. Now we have reduced and we have just economized. We have our efficiency increased. We have come up to 30%. Thank you.
Thank you. Thank you, Mr. Charles. May I request Mr. Shankar Narayanan to present a small memento on behalf of our Refcold India team. Thank you so much, Mr. Charles, for sharing.
Thanks for the opportunity given. I don't know whether I have just, I just reached all over your requirements, but what I require from the industry.
Of what is in the milk industry.
Good.
Thank you. So now, I think we are now at 3:30 now. So we have a quick and brisk, 15 minutes break for coffee, tea. And we have the next session starting at 3:45. The speaker, Dr. Alex, is already online. So I think once you have your coffee, You can just move in quickly here and then we can start the next session.
Sí.
Hello. Yes, hello. Dr. Alex, can you hear me? You are on mute. Please unmute yourself. We have just, yes.
Hear you.
Can- Good, okay. So we are just having a short coffee break for 10 minutes and we should be ready in the next, I'll just tell you, in the next about 10 minutes from now, we should be ready to get going.
I just have a little bit of lunch and then I'm ready.
Yeah, sure. So we just stay online and in 10 minutes, we begin the
Yep.
talk.
Yep.
Thank
So, das ist in Mann. Ja, men det skal jo også jeg forstå, at
Jeg har fortalt dig mange gange, jeg har en lille hjerne.
Jeg lever jo det hele. Jeg forstår, at du stadig går derover, for det taler. Jeg kan høre, at det taler. Det gør godt. Eller det skal bare. Ja, du skal have et glas vand.
Du må gerne sidde og høre. Ja. Ja. Og så.
Luk døren.
Ja. Tusind tak. Ja, det er godt, da.
The next session is going to start. Ladies and gentlemen, the next session starts at 3:45. Kindly take your seats.
Good afternoon, everyone. Welcome back after a small tea break. Welcome, Dr. Alexander. Alex, we are looking forward to listen to you. There's a lot of delegates here in Refcold India program here. Looking forward to listening to your presentation. Yeah, over to
Talk 124. Safety standards and troubleshooting of refrigeration plants. Dr. Alex, Global Consultancy, APS, Denmark. Dr. Alex has been working at JCI since April 1st, 2000 as the technology manager. He specializes in the design, development, safety, troubleshooting, startup and commissioning of refrigeration equipment and systems. He has been instrumental in developing compressors for ammonia, hydrocarbons, carbon dioxide, and water refrigerant systems. In the last 40 plus years, he has been working towards environmentally friendly solutions to the many challenges faced by the refrigeration industry and novel ways to use refrigerants. We welcome you, sir.
Thank you, and thank you for having me. Thank you to the organizers of this very nice conference. And let me get started. Safety is very much in heart of everybody. We don't want to see anybody get hurt, and we are actually have our human right is to go home from office or from work in the same shape as we went to work. Means that you are, of course, you can be a little bit tired, but that's not about it. It's more the safety issue. Safety is an integrated part of the refrigeration, and while we are talking about phasing out in different working fluids, it is also very often discussed that some fluids are flammable, some of them are perhaps even a little bit toxic or something like that. But if you follow the standards and guidelines, where the purpose of the guidelines is to ensure the safety, then you will have no problems with the insurance companies. They will, if you follow the standards. But if you don't follow the standards, you will have to prove that the solution you have chosen is better and more safe than is prescribed by the standards. If then the authorities or the insurance companies, they deem your solution not safe, then you are in trouble. Let me say it straight to you, accidents is not something that just happen out of the blue. It is actually something that is caused by something. And there are, if you go up in the helicopter and look down, there are three main broad reasons for accidents to happen. There is the technical glitch, means that the design has not been as it should be, or the products are not as they should be. Or there's a human performance, means that you can be tired or you can be distracted or many other things. Or missing barriers, meaning that you can limit people. Actually, in the standard 5149 ISO standard, it says that only competent persons can go into the machine room. It has to say on the door, so you don't go in if you are not competent. The problem is many times people don't know what is competent, but we can come back to that. There is a guy called Herbert William Heinrich. He invented this triangle to the right. Sorry, he invented a theory, and he says that behind every accident there is a cause, because accidents don't happen by themselves; they are caused by something. Accidents, they are also for the 70 or close to 80% caused by unsafe acts, means that you have done something that you should have perhaps not done. I'm not saying anything about doing something stupid, but something that you should have not done. And then 20% of the accidents, they are because the conditions were not safe, and then something happens. Here you have this William Heinrich's triangle. The bird, the Frank Bird, he actually later...
To stay competitive, fleet...
Sorry for that.
No worries. It's about the what do you call it, the underlying data, because the data, you can go as deep as you want. You can see to the left, they can go into near miss and all this, but near miss situations, which actually is also something that you should discuss internally in the company, they are never really reported, and that is why that the Heinrich triangle is actually the most likely thing to see, because that's what you can start to record, because near miss also means that you actually get an accident that actually happens, but it's not a serious, what do you call it, injury you get. So therefore, they are recorded in many times. This Heinrich, he also published a book, Industrial Accident Prevention, and I saw on the internet today that it is costs around 100 euros. You can see here the price of the book in 1931 was $4, so it's peanuts. Things have changed since then. Also, when we look at the different working fluids or refrigerants, some of them are flammable, they have different auto-ignition temperatures, and they also have the different values for when they ignite or become toxic and all this. And these data, you have to keep in mind, I don't think you will remember anyway, but the lower flammability is very important. For the next slide, I will show you, because the lower flammability is the safe zone. When we go into the standards, they will talk about zoning, especially when you are over A1 level, means that if you have A2, A2L, A3, B2, B2L, and B3, there is a few, then you have to ventilate according to another paragraph in another formula than there is in the ISO 5149 part 3, part what do you call it, chapter 5. You have to go to the 5.3. It says that you have to go to the IEC 60079-10-1, and there you can actually start to classify your zoning. So there is a possibility, but if you stay in lower than the lower flammability limit, but remember that the lower flammability limit is not a fixed data as very often you see when you see the data I showed you just before in the table. It's a fixed point, but you can see it's a moving target. Also, the auto ignition temperature depends on pressure and on temperature. So it's not so simple as we very often do it. But anyway, if you ventilate, you are safe. So the key word here is ventilation. The standards, they set out a number of rules. There is, of course, everybody, or not everybody, but many of you have perhaps heard about 60355-2-40, but that's for more indoor and smaller systems, say up to 12 or something kilowatt, where everything is built into the same box and you have the electricity making the biggest issue. But if you have a big system, saying industrial or semi-industrial, you place the unit outside, that's one, and you can also place the control cabinet outside, so you only have very few components in the zone that you need to mitigate and how to do that. And there you use the 60079-10-1 as I show here, and then you can also use the 5149 for calculating the ventilation. The 5149 says that you have to use the max 10 kilogram released, and then you can calculate from there. But the zoning makes it a secondary release in a refrigeration system. And it is because we have a limited amount of refrigerant in the system. Don't compare the zone 0, which is constant. That is for petrochemical sites. We are not a petrochemical. Of course, if you put the unit into a petrochemical site, then it's a different story. But we are here in safe zone, and the only zone we have is in the machine room, which we can limit in size, and we can ventilate this. And that is where we take away the heat, or we can take away the fuel, means the gas. We ventilate it away. The oxygen is not so good to take away because we need it for breathing when we go into the machine room. When we talk about the qualifications, previously the EN 13313 was the qualification standard, but it's now lifted up to the ISO, and it's going through the process of being integrated in the different countries as a qualification requirement for working from design to decommissioning of the unit. What does the different people working on the different types of thing do? That's described in this 22712 standard that is coming. It is already implemented in many countries, but I think it is coming also to India very soon, if not already. But it is very important to, if we have to do this decarbonization in a safe manner, because we can also do it very quickly and then take in non-qualified and then see how many that will actually be injured. That is not a good idea. So the classification, according to the 60079-10-1, it is about continuous, as I said before, zone 0 is continuous release, means petrochemical, or primary grade means also release it is a zone 1. It can be a petrol station, it can be around, when you go and fuel your car, actually you're standing in zone 2, but you have a zone 0 just around the fueling and all this. But it's well ventilated, so you are far away from anything, so that's safe. But as we will see here in a moment, you can ventilate yourself out of almost anything, and you will always be safe. So therefore, it's very important to be aware of ventilation. Where are you? And where am I blowing away safety valves if they are open? Or if I'm ventilating the machine room, where am I sending it to ventilate it? It has to be a place where there is air movement. It's not a good idea to ventilate into a place where there is no air movements, then better have a chimney and blow it up in the air. Then it's easily dispersed, and that is what it's all about. Making the concentration lower is the key. Here, we have the standard here. I've snitched out a little bit. I don't know if it is actually a legal according to copyright things, but you have here some idea about secondary release grades, and you can calculate. You have to calculate for the secondary releases. You have to look at one of the. You're not obliged to calculate all, but you have to look at the worst release that you can foresee according to this list of possibilities. And it's very often a valve, because valves have a stem and that can leak, and there you have to select that here. And then you can say, I ventilate and this will leak so and so many grams or kilos per year. And in this way, you will actually know exactly what zone you are in, and it will almost always end up saying that you are leaking less than 50 kilo per year, which is actually the limit of many detectors. So you cannot even detect so little, but you have to ventilate for that, and then you can in this way. If you ventilate according to the standard, you will not ever be able to measure anything, because as soon as you measure just a little bit, you go up in higher level of ventilation, and then called emergency ventilation. It's up to 15 times the room or the free area in the room, and the ventilation rate would be so high, so you will never be able to measure anything unless you have a gas chromatograph, which makes it ridiculously expensive to do. Also here, you can see the grade of releases. If you ventilate with good ventilation over to the left, then you have non-hazardous zone, even that it is a continuous zone, means a zone 0. But by having a zone 0 well ventilated, then you are in safe non-hazardous zone, and in this way you are safe, and that is what it's all about: safety. And it's safety for the people working there, for the products, for the investment of the consumer, for the owner, and also for the products and the people working there. So there is many people in this drama. If we're talking about ammonia, then we have a different thing that on top of this, where ammonia affinity to water can be used. This I have borrowed from the RTOC report, and it shows you the principle in a cooling tower. It doesn't show a pump vessel, because you can connect a pump vessel, you can add some acidity and keep the pH value around 7, means neutral. Ammonia, as we know, is a basic refrigerant. So if we just absorb a lot of ammonia in the water, it will be very basic, this water, and that is not also very healthy. So therefore, we need to add some, for example, sulfur acid is a popular way to put it in. And then you can, when the capacity is used, you will have to dump it as chemical waste. But you can clean the air, so it is almost not detectable, or not detectable with the human nose. Can be that you can detect it with a gas chromatograph, but it's very little, and it's well proven. And I think it is used in many places, especially in rural areas where you want to avoid problems with neighbors. I know a lot of the big companies worldwide that have installed this when they are close to living areas for people. Safety around non-flammables. It can be CO2, for example, or it can be other gases that I will not mention here. And they deplete the oxygen in the machine room. So it's very important that you have a detector on you that can tell you that what is the concentration around you when you go into the machine room. But before you go into the machine room, there should be a display outside the door that tells you what is there a concentration in the machine room before you go in, because we have seen sometimes that the concentration, the people have gone into a cold room or into a machine room, and then they close the door and they drop over and lifeless. There is no life, and that is because the oxygen has been depleted, for example, by CO2. And therefore, it's important that there is a detector and you can see it from outside. If there is a level, you have to know, is it going up? Then you have to take your precautions. If it is going down and if it is safe, you can go in. But otherwise, you will have to have full breath protection, means bottles on the neck, and then you go in and do it, find out what is wrong, and then you ventilate again. It's about ventilation all the time. That goes for all A1 fluids, but it goes for all refrigerants generally, that you know what you're doing, before you go in, you have to know. There has to be a guy at the door that follows the level. Is it going up or down? There can be pockets or clouds in the room. Don't go into the clouds because it's a two-phase phenomena. It can be very low oxygen, and then you still have a problem. So ventilation and monitoring the levels is the key here. Leak detectors, they are very often sold as being able to detect 5 grams per year. But if you look into the standard, you will have a description very precise that if you have a leak, you have to take the detector over the leak 10 times, and there must be no air movements in the room. Already here, we can understand there is an issue here because we have a ventilation rate when people are in the room or machine room of at least about 4 times per hour. So there is already a movement in the air. If you are outside, it's totally impossible to control this. So in practical experience, the lowest leak rate that you can measure is around 50 kilos. And it is the most realistic you can do. You can do it with soap and bubbles. But again, if you're standing out on the roof and it's a windy day, the bubbles will blow away before you see anything. So it's a tricky thing to find leaks. You have to do it in a very calm place, and you have to follow good practice. And good practice is actually looking at, is there any oil coming out with the refrigerant? Because if there's oil coming out, you know there's something wrong because it should be inside, not outside. If you didn't know, it's a secret, don't tell anybody. Accidents is integrated part of life. We all take a risk here and there, and in this case, it's not a good idea to take the risk. You have to step back and see what can you do to minimize the risk so you know what you're doing and where is the risk. Some of the most common falling risks, this is the final slide. The most common cause of accidents is actually fall from height, and that's where we come back to the barriers. There's no sign showing don't go over here, or this is not safe to walk on, or something like that, and then people go out or with a truck and then they fall down. It's seen so many times. So therefore, following the standards, it's a good way, but you still have to use your common sense, and you have to evaluate the risk and what type of risk it is, and try to stay safe. Thank you for your attention.
Thank you, Dr. Alex. It was a very nice session. As you know, generally they tell the technicians, keep your eyes, ears, and nose, and the touch, feel also. Be very active when you enter a plant room, because a technician can't just enter without ensuring that those are enabled, because you can feel a lot of things through that.
It's rarely a good idea to walk around with your head under your arms. You have to have it on the right place and use it for something.
Any questions from Because you have a full packed house here. I don't know, we are able to show you a snap of this. Any question? Yeah, there is a question from one.
Vijay Bhaskaran from ex-Abro, India. So, yeah, see now ammonia is a future refrigerant, according to me, but people are very panic and they are literally worried about how to use ammonia and all. So can you throw better light on this?
Yeah, ammonia is a fantastic refrigerant because it's self-alarming. That is the good part of it. Ammonia is the most efficient refrigerant we have, and it has been used for more than 150 years. And there is absolutely no reason to be afraid of ammonia. We see very often records of the releases happen where people are sent for observation at the hospital. But what you don't see in the newspaper is that they are actually just gone in and then they're gone out again. So it's just that they are irritated. And we have to be very clear about this, that there's a difference between being in a critical concentration, which is much higher than we think, and then being irritated. And it's natural to be irritated in your eyes, in your throat, you cough, your nose is running, your eyes are running. But it has nothing to do with a dangerous concentration, because dangerous concentrations is more than 1,000 ppm, but already at 100 ppm, most people are running away.
Yes, thank you.
Thank you, Alex. Particularly, this is Sukumar Devota speaking. And thank you very much for accepting our invitation and giving a very wonderful and informative lecture. Thank you.
My pleasure. It was a pleasure, Sukumar.
Thank you. I think we have our next speaker, Mr. Alpaslan Terakil. Welcome you to our Refcold India technical seminar session. He's going to talk on a very nice subject, which is how to handle natural refrigerants in commercial refrigeration systems.
Talk 125. How to handle natural refrigerants in commercial refrigeration system. Mr. Alpaslan, Application Manager, CCOP, Turkey. Mr. Alpaslan has been a dedicated professional in the refrigeration industry since the year 2000. He began his career as a quality engineer with BSH, a leading manufacturer of home appliances, and in 2005, he moved to its pre-development department in Germany. In 2015, he joined CCOP, a renowned compressor manufacturer, and is currently working as an application manager. He has consistently prioritized technical competence, a comprehensive understanding of customer requirements, and supporting them in making informed decisions. We welcome you, sir.
Thank you very much. Thank you for this opportunity. Thank you to organizer. Actually, Dr. Alex covered most of the part of my presentation, so we can make some chit chat. Okay, everybody can hear. So I think most difficult. No, this is not me. This is Omar. My name is Alpaslan. Okay, it's not easy to remember some strange name. Alpaslan is a real old Turkish name, but I can tell a story about when I was studying in UK. I was living with old couple, and they had lovely grandkid. Lolly was 6 years old that time, and she came to home. I love kids. We play a lot during the day, and after dinner, just dinner, she went to sleep, and I went out. I was a young guy, and till 4 o'clock, I was in the nightclubs. Back to home, it was in the morning. I think I had 2 hours sleep, and she was jumping to my bed, and she was shouting, 10:30, wake up, playing time. I checked the watch, it's barely 7:30. I said, it's 7:30, it's not 10:30. No, you are 10:30. No, I'm Alpaslan. The sound is the same, so you can keep in your mind now my name. Okay. natural refrigerants, why we need them. It doesn't move. No. Okay. Next one. No, I cannot move with this one. Or we just say next. I'll move the slide for you. Okay, would be nice. Okay, then next. As mentioned, I'm coming from SecOp. I'm working since 2015 as an application engineer. I'm responsible of half of the work coming from Africa, India, up to Bangladesh, Pakistan, a bit Russia and Turkey. What I will present today is how to handle F-gas, flammable gas, that you will use eventually, not now, as far as I have seen. Next, please. So who we are SecOp. We are a provider of hermetic compressor for small application. And yeah, we are producing compressors more than 60 years. We have light commercial compressor, AC powered. We have battery-driven DC powered compressor, and also we have a special department medical, let's say, freezer and fridge dedicated compressor. I think this is the unique of SecOp. Next one, please. So 3 segments: stationary cooling, mobile cooling, and medical cooling. Next one. Yeah, refrigerants. At the moment, what I have seen in India, you are using mostly R134A and 404. Are there any producer here? Any appliance freezer, fridge producer? No, nobody is producing. Okay, so most of the producers are using R134A. I know some household application in India, they are using already R600 since many years, but most of the light commercials are 134A and 404. Available natural refrigerants, alternative refrigerants are R290 and R600 and R744, which is CO2. If we compare these old, let's say, HFC gas with available refrigerants, natural refrigerants, actually they are fine, but global warming potential of R134A and R404 is pretty high. That's why they will be banned. They will not be in use for the future. It will not be today in India, as far as I can see, but it will come. And maybe you should keep in your mind to make a project to switch from those gas to flammable gas is not one-day job. So it will take 2 years at least. So you need to start development from now on. Next one. How is the situation in Europe or the rest of the world, let's say, Europe and US? From 2025, those R134A and 404 will be banned. The other HFO gases will be banned from 2026. Only 3 gases will be left, and the gas charge amount was limited like 150 gram. Now it's increasing to 500 gram for light commercial applications. It will be free after 2025. How it will be in India, I'm not quite sure. I asked to producer, I asked to my friends, but I'm pretty sure it will come because, you know, this global warming potential is important parameter. And at the moment we are suffering with this global warming issue. So it should be here in short time. Next one, please. Okay, those gases have also advantage. It's not only global warming potential point reduction, it has also function on efficiency. Appliance efficiency will be increased, so energy consumption will decrease on same appliances, but it will help a lot also for the environment. Those gases are flammable. How flammable is A3? So, for example, R290, if we have released 38 gram into 1 cubic meter, this is the limit of ignition around 450 degree. R600 is a bit higher. If you release 43 gram in 1 cubic meter, is the limit of R600 flammability. If we compare the efficiency, COP, of the gases, R600 is most efficient gas at the moment. And then under the, let's say, R600, R290, and 404 is coming. And if we compare, R22 is coming. And if we compare with R404, 404 is the worst gas on COP level. Next one. How to change? This is an important part, but I don't see any producer. Just for information, you need to change your product, you need to change your production, and you need to change also after-sales service. So this parameter has to be changed. That's why it's not one-day project. You cannot change your application from one day to other day. When it comes, you need to have your project on product design, your production design, and after-sales service. Next one, please. What you will change on your application. First, we have safety standards. As Dr. Alex said, safety standard is same, 60,079 ISO standard. Compressor selection, so you need new compressor because conditions are different, compressors are different, the motor design, valve design is different. Then you need to change flow, basically capillary or whatever you use to control your flow, you need to change. Gas charge determination, it should be changed. You cannot charge same amount of the gas into system, and also some small changes on evaporator and so on. Let's go on safety. Next one, please. Yeah, the main rule is make a border between gas source and ignition source. Gas source are easy, the tubes are gas source, compressor itself, gas source, any component who has refrigerant inside is gas source. Ignition source are electrical component. So basically, when you separate these two, you would not have any problem. In the kitchen, any household appliances, you don't have any problem because 38 grams per cubic meter, even small, let's say kitchen, where you put your refrigerator has already 5 to 10 cubic meter area only around of the application. Kitchen is bigger, so you cannot reach this level. Household appliances has 150 gram limit. If you release all of the gas inside of the kitchen, there will not be any explosion. Then there will not be any fire case. But inside of the application is much more important. Inside of the application has limited 400 liter, 300 liter, whatever. So inside of appliance is much more important in our case. If there's any electrical component inside of the appliances, it should be isolated from gas source. This is the safety rule, what you should keep in your mind. Next one, please. Yep. Compressor selection is easy part. When you are using old compressor, check the data sheet and find your cooling capacity and take same compressor, same cooling capacity with flammable gas R290. Here we have example SC10 CL, which has 400 watt cooling capacity with 404 gas, and alternative is KLF 7.7 CND with 384 watts. It's a bit lower, but it can cover, no problem. So by that way, this is while you are using compressor with 404, 134A or whatever, you can choose new compressor with flammable gas. Another method is, next slide, please. Okay, SECOP has heat load calculation on internet. You can reach by, let's say, this link. So heat calculator makes basic calculation, simple calculation for cooling capacity needs according to ambient temperature, the target temperature inside of the compartment, load if you have, let's say, pull down load or any additional component like fan inside, heater inside. So you can make rough calculation and you can choose your compressor accordingly. In that case, we found 387 watt cooling capacity needs, so KLF 7.7 can cover it. So this is compressor selection. Next one, please. What is also important, the gas itself is flammable, but if you compare with HFC and flammable gas like propane, butane, the bonding between carbon-carbon and hydrogen-carbon are almost same. So during running with heat inside of the compressor, the carbon-carbon atoms can be bound and make a graphite configuration. And this graphite configuration close to fuse side, these pins, that can make arc, or they can make heating. This part is same for all compressors. It doesn't matter any brand. So this graphite form can heat this glass part and make a crack and get gas release. So to prevent this, SECOP has, let's say, solution. We are we are the only producer at the moment who has solution to reduce this risk. We have cover on it, and we made a test many times. So it says test result says we are safe on this graphite building on the fuse side. So that could be important point to select your compressor. So if the compressor was not developed or not developed, it's born for flammable gas, is different than convert from let's say 404 or 134A. We know some compressors are just convert from all gases to flammable gases. This is one of the important point for the compressor. Please, next one, please. Capillary selection. So definitely you need to change your flow rate because the density, nominal density of the gases are different. So the different number of molecules you are sending by different flow. We have solution for that. We have at the same page, at the same link, we have capsule application. You can give the gas type. We have also all gases are 134A, 404, can't remember, R600, 513, whatever. We have lots of gas inside. You can calculate what should be capillary. This is the starting point, but at the end you need to test and confirm these results. Charge determination, again, due to different density of the gas, you need to put different, let's say, gas amount in the system. The best way is test and see. So basically, we are putting 3 thermocouples on the evaporator, one of them insert of the evaporator, so beginning of the evaporator, just after injection point or brass point, one of them middle of the evaporator, and at the end of the evaporator. We are measuring at the same time power consumption and suction tube temperature. Suction tube temperature is important. Don't put the thermocouple close to compressor, then you will sense, or your thermocouple sense the compressor temperature. So it should be at least 150 millimeter far from compressor. From this measurement, we are adding gas step by step, and we are seeing the temperature of evaporator inlet and evaporator outlet is coming together. That means evaporator is fulfilled in certain or desired conditions. And suction tube, let's say, temperature is around ambient. That's also important. If you make cool your suction tube, that means you are shifting cooling capacity outside of the application. That we don't need, that we don't want. This is not efficient application. Power consumption, you can also see it will rise up a little bit from the beginning, because at the beginning you have less gas, almost no cooling. When you increase the gas amount, you will have some power increase. At the end, you will see optimized point, then it will rise up. So just before this point, this is your nominal charge point. And according to your process tolerance, could be plus minus 1 gram, you can set your process tolerances, and you can say, okay, this is charge amount for this application. Next one. Production, okay, production, this part was covered by Dr. Alex, thank you, because I was thinking how to explain zone 0, zone 1, zone 2, that was really difficult, and yeah, let my best regards to him. Okay, we have limits like 38 gram per cubic meter, so 15% till 15% of this limit is green area, so you don't need to anything. Till half, you have, let's say, you should do something. But the main, let's say, factor or main action is ventilation. If you have ventilation in your production, is the best way to get rid of any leak. What you should know, those gas, R290 and R600, are heavier than air. So ventilation should not be on the top, or on the roof, should be on the floor. Also sensors. Basically safety sensor should be on the floor. When the gas pour, when gas leak on, it's okay? Okay, when gas leak, it will go on the floor and you should sense on the floor. Basically, you should put sensor on the floor and you should ventilate air from the floor. What is important, this is also one of the better experience, if there's a hole or channel on the floor side and the sensors cannot feel, but the gas is accumulating there. When you have, let's say, arc around this channel or hole, there will be really explosion. We have seen this, and actually this area, the zone up to 10 meters, let's say, this area should be flat. There should not be any hole or channel. This is important. Yeah, we can go next one. That was easy. Yeah, zone 0, zone 1 was explained. Here again, lots of, let's say, potential protection is there. You can put more than one sensor. It should be more than one sensor, actually. If one is failed, then the other will warn you. There are many items you can add, visible sign or whatever, but the ventilation is much more important because workers can see if ventilation is there or not. So if there's a ventilation of stops, worker can warn you there's ventilation stop and he can stop the system. So most important part is ventilation for the production. Let's go next one. Okay, yeah, gun parking is important. So if you make, let's say, a wrong design of your production on gun parking, this is charging gun, and you would have some leak and accumulation on the floor. That would create a problem. Next one, after sales service. So basically, what you are selling to customer has flammable gas inside, and your after service should know there is flame gas. They should not use torch to open the system because it will create a real big accident and harm for him. So what you can use, actually, there's a solution for this. Next one, called by Lockring, this Danish company. Yeah, use cutter and use Lockring. So basically, it ties tubes without any flame, any brazing. There is a material, it's a glue, let's say, put on the tube and make a connection with the ring. There are two types of ring or two types of material. In the next slide, we will see aluminum one and brass one. With aluminum one, you can tie aluminum, steel, aluminum, copper. And with brass, copper, steel, or steel tubes connection. So that could be solution for after sales service. Lockring is the Danish brand name, actually, but it's like a, yeah, there's other brands, but the idea same behind. Okay, yeah. And also in my laboratory, I'm using. What I can tell is not only production is not only product itself, the laboratory where we built in Turkey, for example, it should be also according to those FCAS. It should be ventilated very well. There should be sensors, more than one. And at the end, if there's a fire case, there should be warning system, and we have carbon dioxide, let's say, system to fulfill room in case of fire. So that's almost done. That was the last slide, I think. Can we go one more? If it's last one? Okay, yeah. For after sales service technicians, if we have, don't use flame to open this compressor when you see R600, R290 and flammable gas mark on it. Yeah.
I just. Hello. Yeah, I just wanted to make a comment. We are using 600A in refrigerator. Almost all refrigerators use 600A. So all the ideas, we are producing 600A refrigerator. And all commercial units now use 290. You can go and see many units made in India being displayed here. There are almost all commercial top brands have switched over to 290. Yeah, so this is the information I wanted to give. And we have been using lock ring in the 290 models in commercial. So all these things are available today in India. So that's all I wanted to say. Thank you.
Yeah, thank you. Thank you so much, Mr. Alex. Can you please? Thank you so much, Mr. Alpassian. It was very nice of your presentation. And may I request any questions from anyone? There are no questions. May I request Mr. Vishwanath Sen? He is from our. No, I think it was very clear. You had shown. Only thing is, what we generally do is we will take the technology part of it, not the brand name part of it, as you mentioned, because that is only for reference that you had given. I think it was very clear. May I request Mr. Vishwanath Sen? He is from our Indira Gandhi Atomic Research Center to present you a memento. It's you have to be there on the stage. Okay. Thank you so much for taking us through that presentation. Yeah, thank you. Thank you, Mr. Vishwanath. Thank you, Mr. Alpassian. Now we have our speaker from Egypt, Dr. Omar Abdulaziz. Yeah, please. Who is online and who is going to talk about designing a high efficiency HC290 chiller for medium back pressure applications for retail food store. And it's nice to have welcome Dr. Omar Abdulaziz.
Thank you, sir. Talk 126. Designing a high efficiency HC290 chiller for medium back pressure applications, retail food stores. Dr. Omar, Department of Mechanical Engineering, the American University in Cairo, New Cairo, Egypt. Dr. Omar is a professor of thermofluids with more than 15 years of experience in research, development, and project management in energy efficient building technologies, sustainable energy production and utilization, alternate cooling and heating technologies, and alternate low GWP refrigerants. He is currently a member of the United Nations Techno-Economic Assessment Panel and a co-chair of its Refrigeration, Air Conditioning, and Heat Pump Technical Options Committee. He is an active member of ASHRAE. He serves on its Research Administration Committee as a Research Activities Subcommittee Chair. We welcome you, sir.
Thank you. Can you hear me?
Yes, doctor.
Yes, it's a pleasure to be here with you. I'm honored to present Is there any background noise or anything like that before
No, nothing. Nothing. Your voice is perfectly clear.
Perfect. All right. So let me share my screen. Yes. All right, so today I'll first talk about the use of propane as a refrigerant for medium back pressure application, and then talk about some design consideration when we're working with propane. This was a project that I conducted in South America about 3 years ago, and talk about the results and comparison against the state-of-the-art HFC technology, showing that propane can indeed be as efficient as hydrofluorocarbon technologies. Of course, distinguished speakers who came before me have probably discussed these, but quickly going over them. Propane is sought as a great alternative refrigerant because it is naturally occurring. It comes as a byproduct from refineries, and it is used everywhere. So people know how to use propane. It is also green because it has low GWP and zero ODP, and also has a very high efficiency. Over the years, people have done pilot evaluation of using propane as a refrigerant and showed that its efficiency surpasses that of the efficiency of R22, and also can be as comparable, if not higher than the efficiency of R14. However, the main challenge with using propane is the flammability. Now, when using propane as a refrigerant, we need to be careful because we have to use it while adhering to HRI standard 700. So we cannot just use the propane that is used in our flammable cylinders. It has to be 99.5% by weight clean. There are very low impurities, especially those C3 and C4 impurities. And also the moisture content should be very low. Now, when we compare R290 versus R22, especially when I want to design it for medium back pressure application, the first thing I notice is propane and R22 are very similar in terms of boiling point at 1 bar and critical point. So this is good from that point of view. And we find that propane has lower critical pressure. That means that it is lower pressure than R22, which means if I use the same gauge of my tubes, I'm fine. However, again, the same issue with flammability and auto-ignition temperature. Of course, this value, the 450, varies from one standard to another, and the minimum ignition energy varies from one standard or one source to another. However, the 0.25 is the generally accepted value. This is thermodynamic behavior of R290, and that's what you see here, the saturation temperature. So if I work with the medium back pressure, so in the evaporation temperature, you will see that the saturation temperature is almost the same. However, as you go up towards the condensation temperature, the saturation temperature is much lower than that of the R22. This has a negative impact on the volumetric capacity. You will see here that the volumetric capacity of propane is lower, sometimes significantly lower than the volumetric capacity of R222. That means that we will have to use larger compressors. This is sometimes what we call a double-edged sword, because using a larger compressor can help us in terms of heat dissipation, because working with a larger compressor provides more surface area for heat to dissipate. However, that means sometimes more cost. And we have to be careful about providing this cost-benefit analysis. I will swift through some of these design considerations because I'm sure they have been very well taken care of. But the first thing is we need to be careful about the material compatibility. We find that R290 is compatible with most metals used in HVAC and R applications. It also is compatible with most plastics and elastomers used. However, we have to be careful that it is not recommended for polyphenylene oxide and nitrile rubbers. It is not compatible with PMMAs and natural rubbers and silicone rubbers. So these are the only considerations that we have to be careful about. In terms of oil compatibility, if you are using the same oil that you are used to, that's fine. However, you have to be careful that it is not compatible with polyvinyl ether, so PVE or hydrotreated mineral oils. It's also not compatible or not has limited compatibility with PAG oils. Now, when we work with or when we try to design a system, right, we have to avoid the flammable atmosphere, avoid the or eliminate the ignition sources, and limit the consequences of ignition. And as you have heard earlier, we have a limited charge that we have to work with, right? So the first thing here that we want to work on is, we want to find what are the dangerous substances, characterize the possibility of flammable regions, and then limit the dangerous substances of the charged mass. Where is this flammable region going to be located, and increase the ventilation. This becomes a design challenge. Eliminating the ignition source, as we have seen in the previous presentation, the fusile was one idea, using ATEX certified components, working around, using plastic fans, making sure the fan does not hit the surrounding and all these things. And then limiting the consequences of ignition. So make sure that there is a ventilation, there would be no overpressure and all these things. So when we design with propane, we have to do CFD simulations, look where would there be a flammable region, do a lot of scenario estimation, like where is there going to be what we call probability, right? That this flammable region is going with an ignition source going to coincide, right? So this is very important, what we call the probability or FTE analysis. And then we have to look at this thing, which is the severity, right? So if the probability is very low and the damage is very low, so the severity is non-existent, so I'm good, right? But if the probability is very high, the frequency of the probability is very high, and it's a lethal damage, I definitely don't want to have operated in this region. So this table is very important to consider when we are designing a system. I'm not going to go over this slide. I'm sure it was covered by my esteemed colleagues before. So as this one. So the integrated safety design principles, we have to minimize the leakage. But then this is the second one that led to this secondary coolant approach, reduce the charge size of the system. How can reduce the charge of the system if you are doing a commercial refrigeration? Using a secondary loop is an approach that we can do. So reduce the amount that may be present in some released or particular area, and use ventilation as suggested by colleagues earlier. Step 2 is identify all the potential sources of ignition and try to eliminate or remove or shield them from the flammable region. And step 3 is to understand the severity associated with the potential ignition. In addition, possible operating faults should be carefully analyzed to prevent dangerous situations and any anticipated misuse of the flammable refrigerant or the operation of the equipment that contain flammable refrigerant. Now, when we design equipment that contain flammable refrigerant, we should adhere to safety standards with medium back pressure chillers for refrigeration. The most relevant standard is the ISO 5149. Now there is a newer version of it, so I think it's 2021. But this slide is based on an early version, which is 2014. And we have to look at two important parameters: the maximum allowable, the maximum charge, and the allowable charge. The maximum charge is a function of the equipment, the location of the equipment, and the occupancy, what type of occupancy or the category of the occupancy. And then the allowable charge is a function of the room size and the refrigerant release location. So we say category A is when basically anyone can be in near proximity to this equipment. Category B is when you have supervised occupancy. So there is someone who knows things about this equipment and the danger that is that can occur from operating or servicing this equipment. Category C is when you have occupancy with only authorized access. And if we work with a category C, that provides us with a lot of really good approach on how to handle the design. So you can see here that if the system is designed with an indirect approach, which means that there is a secondary loop, then we have a much more leeway in terms of how much charge you can put in the system, because there is now no limit of refrigerant charge. Of course, if you put the refrigerant in the system, then there is this 10 kilogram charge limit. So most manufacturers would always prefer to keep this 10 or 25 kilogram per compressor circuit as the limit when operating with flammable refrigerant. So as a designer, how can I design a high efficiency system, but also minimize the charge? So the first thing is, I want to pick the compressor that has the smallest internal volume technology. So I'm not going to use a screw compressor. I'm going to use a rotary compressor, a scrub compressor, or a hermetic reciprocating compressor. I'm also going to work with my supply chain and identify compressors that have the smallest suction chamber, work with compressors that have oils with low refrigerant solubility. So it's important to avoid having refrigerants that have high solubility. In terms of evaporators and condensers, we want to minimize the charge available in these heat exchangers. So if I'm using air to refrigerant heat exchangers, these would be small diameter tubes, like the new technology, the 4 or 5 millimeter diameter tubes. And these technology would definitely require some heat transfer enhancement techniques, including variable fin density or internally enhanced grooving. Also, there is this microchannel heat exchanger technology. Of course, the microchannel heat exchanger pose some challenges, especially in some parts of the world when you are in proximity to the seashore due to challenges with salt in the air and stuff like that. However, there are a lot of advancement in terms of surface treatment and new ways of how you can treat your heat exchanger or add new surface how do you say that, treat your surface so that you avoid any kind of corrosion. If you are using water or fluid or liquid to refrigerant heat exchanger, of course, it's advisable to use a plate evaporator or condenser. These plate type evaporators or condensers need to be designed with the highest possible heat transfer enhancement so that you can minimize the charge. Also for the lines, the connecting lines, we have to be careful because connecting lines can contain a lot of charge, especially the liquid line and the suction line. Of course, with 290, the viscosity is not that high, so we can go with a smaller, like higher velocity in those connecting lines. And if you optimize the piping design, we can reduce the charge by 15 to 40%. Finally, the liquid receivers, which are and suction accumulators, need to be designed appropriately. Now, the main topic of today, the secondary loop system. So we said we want to minimize the charge so that the manufacturer is comfortable to introduce this propane technology for his consumer. So what did they do? We have worked together on having completely isolating the propane cycle from the cooling or the load cycle. In this case, we have a compressor, a micro-channel heat exchanger, and a brazed plate heat exchanger. So now we are using the lowest possible charge heat exchanger for the air side and the condenser, the lowest possible charge heat exchanger for the evaporator. And for the compressor and the fan, we used the highest possible efficiency. So the compressor, we used an inverter technology. And for the outdoor fan, we also used ECM motors, ECM electronically committed motors with variable speed technology. For the load, we used glycol loop with a centrifugal pump. This pump was also running using ECM so that we can have the highest possible efficiency. This is a schematic diagram, and you can see how the fan looks like. To avoid any potential sources of sparks, this fan is designed such that it is made plastic housing, plastic blades, so there is no sources of any kind of sparks, and also ECM, so there is no sparks inside. And you can see here that this room, right? So we have the side, this part is where the refrigerant is, and where you have on this side, this is where you have the air, and it's completely separated. So there is no potential for refrigerant leakage. And we did a lot of emergency blower so that if the refrigerant leaks, there will be a leak sensor that leaks from that sense from the bottom that there is a propane, and this emergency blower will suck the propane from the bottom outside, as you can see here. Now, if I want to model this cycle, I have and achieve the highest efficiency, building cycles and testing them is going to be expensive. So we used available modeling tools. In this project, I used an online tool called the heat pump. It's the Oak Ridge heat pump design model. It has ways to model microchannel heat exchanger, brazed plate heat exchangers, pumps, outdoor blowers, and everything. And also you can model inverters and inverter compressors. Here we can also model ambient air. This was done for South America, and we modeled at dry bulb air temperature of 37 degrees C, absolute humidity of 0.12. Now, this load is a medium temperature, so the return temperature was 0 degrees C, and the supply temperature was -2 degrees C. For the compressor model, we use a variable speed 10 coefficient model. The microchannel is a single row model, and the brazed plate was, as you can see here, this is the model. For the blower, we had a variable speed blower that can provide different mass flow rate or air flow rate because we had to use different heat exchangers. This is basically how the system looks like. And you can see there is almost negligible pressure drop in the connecting lines if they are designed right. And also because, as you can see here, we have very small length for the connecting lines. This is the microchannel condenser. And you can see we have for the R14A and the R290. R290, the air side, we had to use slightly different microchannel, and with the slightly different microchannel, we end up with a slightly different pressure drop because we used we didn't have to use as the same fin density as with R14A. And the main reason for that is R290 was more efficient as a system, so the heat rejection was lower. So when you have lower heat rejection, you would not need as much heat or fin density, and at the same time we end up with using lower airflow rate. So with lower airflow rate, different fin density, we end up with different pressure drop on the air side, and that was significantly better for the capacity and COP, of course. For the compressor, we have the variable speed compressor for the baseline, and for the R290, we used two different compressors. Both of them were scroll compressors. Now, if I want to model a medium back pressure system, this system is going to sit outdoors, and if this system sits outdoors, it has to be modeled for different temperatures. And to do that, we had to work with the lowest possible temperature all the way to the highest possible temperatures and see, what would be the performance on an annual basis. I cannot just model and see, okay, at 35 degrees C, what would be the performance? I need to see the performance on an annual basis to say, yes, R290 performs better. So because we are working with a variable speed, we looked at the R14A versus R290 for different RPM, right? Here, this is the capacity, and this is for R14A, this is for R290. And you can see here that the capacity of R14A and the capacity for R290, the capacity for 290 was slightly lower, to be completely honest. However, if you overspeed, you can achieve the capacity that you need, right? When you look at the COP, now you find that the COP of the R290 is higher. So if you look at the scale, it's 1 to 4.5, 1 to 4.5. But the colors for R290, which reflects, so the darker the color, right, the better the COP. So you find here that the COP for R290 is better than the COP for R14A. Now, the system charge is another important thing. So we want to operate with lower system charge for R290. So we design the system so that we can, first of all, we want to avoid having large variation in charge, because if you have large variation in charge, you need to design a system with a large accumulator. So you see here in R14A, the change in charge is between 2.5 and 2.9. So you need to put an accumulator that can support having a charge of about 0.4, right? The same thing here. This is about 0.3 kilograms of charge variation. So it's a little lower in R290, but the charge in R290 is less than it's less than 35% that of the R14A. When we look at the R14A operation at maximum COP, you can see here that for the different bins, the ones that are highlighted here are the bins that are the highest, or the bins with highest frequency. We see the system COP here, 3.35, 2.89, and 2.62. For R290, we find that we move from 3.35 to 3.59, and then from 2.89 to 3.05, and from 2.62 to 2.74. So while this improvement is not significant, it's about 5% or 7% improvement, it is all the while important to highlight because R410A is considered as state of the art. And I'm comparing best-in-class compressor for R410A with what is available as a compressor for R290. We know for a fact that R290 is still an evolving technology, whereas R410A is an established technology. So when you compare as best-in-class established technology with an evolving technology, and you find that R290 is still better or can be designed to be better, and everything else is the same. You are using the same ECM fans, you are using the same technology, microchannel, the same brazed plate heat exchangers, and still R290 comes better, then this is good for us. This just tells us that we are on a path to showcase that R290 can prove to be better for the consumer. So to conclude, R290 design measures for safe operation for medium back pressure chiller operation are well established. We know they exist. They just need to be implemented. R290 chiller with secondary loop can achieve 4 to 7% more efficiency than typical HFC technology with significant lower life cycle time performance. And the low charge technology and advanced control further improve the system performance. With that, I'd like to thank you and thank Dr. Sukumar Devuta and the organizers for inviting me to be part of this distinguished conference. Thank you.
Thank you. Thank you, Dr. Romer Abdulaziz. It's very nice presentation from you. And any questions, any observation, any points anybody wants to share? So if there is nothing, then thank you so much for accepting our invitation and presenting and sharing your thoughts and a very detailed case study on designing of 290 R290 systems. You've gone through in depth and shared with us everything. Thank you so much, Dr. Abdulaziz.
It's my pleasure.
Omar, it's Sukumar thanking you personally for accepting our invitation. Thank you very much for spending time with us. Thank you. See you soon.
Sure. Thank you.
Good evening, gentlemen. So it's been an intense day of technical discussions and knowledge sharing. I request Professor Sukumar Devota to please come onto the stage to hand over a memento to Mr. Subramaniam, who has been the session chair for the day, and he has handled the session so well that we have completed slightly ahead of schedule. And I have to thank all the speakers as well for sticking on to the time schedules and ensuring that there is no spillover. Mr. Subramaniam, please. Yes, sir. I request Professor Sukumar Devota to please give the concluding remarks for the day.
Yeah. Thank you, Mr. Shankar. I'm not going to take much time because we are at the fag end of the day, tired after day-long proceedings, but still, I thought I'll just summarize it very quickly. We started with a beautiful group presentation from on Indy Plus. There were presentations on ammonia, CO2, carbon dioxide. It was a very highly technical and very interesting presentation, followed by a presentation from other people, including in the afternoon we had the first lecture by Arvind Surange, who is an excellent design engineer for ammonia. He has been installing ammonia systems day in and day out. So his experience with respect to ammonia, particularly on sustainable way, net zero cold storage, very interesting concept. And he was even going beyond saying that we should look at net positive, not net zero cold storage, but net positive cold storage. So I like that idea. I have to use this in my future lectures. And the next presentation was on by Lambert Kuipers from Netherlands, a good friend of mine for a long time, since 1990. And he was the chair for quite some time. And he wrote the 2022 UNEP report, Sustainable Refrigeration. So that's the reason we invited him to speak on sustainable cooling. The next speaker was Mr. CP Charles, and he was an out and out field man, and he gave it a beautiful presentation on challenges in dairy and process and storage. Alex Pache from Denmark. He is an authority on safety, particularly with respect to ammonia and hydrocarbons, and I have worked with him for a long time. So he gave a very beautiful presentation on safety aspects of the flammable refrigerants, particularly with respect to ammonia and hydrocarbons. The next speaker was Alparslan Tarek from Turkey, and he gave a presentation on use of R290 on in commercial systems. And I must say that we have quite a few units being displayed here, one with R600A for domestic refrigerators. And then we have quite a lot of commercial refrigerators on display with propane. So it's just a kind of informative lecture for us, but already it is being extensively used in India, because all our refrigerators are using cyclopentane as the blowing agent and hydrocarbon 600A isobutane as the refrigerant. In commercial, again, cyclopentane is the blowing agent, and so it's HFC free sector, I would say. And finally, Omar is he had worked extensively in Oak Ridge National Laboratory in US until he returned to Egypt recently, about a couple of years ago. So we invited him to speak on his experience with 290 on the comparison studies he had made with the 410A. And so all these lectures were, they were giving some insight into refrigerants, particularly it's a Refcold, so we concentrated more on cooling. So I think it was an excellent session. Personally, I would like to thank all the speakers for their effort and sharing their knowledge. And also, I'd like to thank Professor Maya and Mr. Subramaniam for conducting the sessions, because having a mixed session is not easy. We have people in presence and then in virtual mode, so we're switching back and forth. So it was a bit difficult. So we had our own technology glitches, but then we managed it finally. So you're safe to go home. Thank you very much. Have a good day. So we'll see you tomorrow at 10. Yeah, thank you. Thank you very much.